Today I'll talk about fusing agents and qualia, work with Chetan Prakash, Robert Prentner, and Manish Singh. Let's see. Now it's not. Huh. Okay, so I guess that's working. Okay. So I'll start with just a brief summary of the talk. Physicists have found that space-time is not fundamental, and they're looking for structures beyond space-time. They've found several structures, including the positive Grassmannian and the amplituhedron. And at the foundation of these new structures beyond space-time are something called decorative permutations. That's on the physics side. So they're looking for stuff beyond space-time. What they found at these decorative permutations give rise to scattering amplitudes. So on the left here is a decorative permutation. On the right is a scattering amplitude. Each one of these dots, the white dot is a 3-particle amplitude. The black dot is the other kind of 3-particle amplitude. From the 3-particle amplitudes, they can compute any Onshell diagram and any scattering that they want for any kind of number of particles. So the physicists have found these beautiful structures beyond space-time, but they're like monoliths beyond space-time. They're just static structures. There's no notion of dynamics and who ordered those permutations and what's being permuted and why. So that's sort of the interesting state in physics right now. Our work is on consciousness and conscious agent networks, and I'll present our model of consciousness and conscious agent networks. What we've discovered is that when we look at n interacting conscious agents, the way to understand their interactions is through a mathematical structure called a Markov polytope M sub n. So we'll look at these Markov polytopes. To try to make a connection with physics, we decided, could we find a way to give decorated permutations to Markov polytopes? It turns out there is, so this is a new contribution apparently to mathematics, that there's a way to classify Markov polytopes and their cell decomposition with decorated permutations. So doing that, we then propose a bridge with current physics. So the physicists have let go of space-time. They've found structures beyond space-time like the positive Grassmannian amplituhedron, and they're modeled with decorated permutations. For our part, we're starting with consciousness. We've discovered that a way to project that down is through Markov polytopes. And we found a new way to describe them with decorated permutations. So we're conjecturing a link between, this is M3, the Markov polytope involved with 3 agents, conscious agents, and we're proposing a specific conjecture of connection with the 2 3-particle amplitudes in physics. So I'll go through that. That's M3, we'll talk about it later. So first, to talk about consciousness. As you well know, there are many interesting theories right now about consciousness, including the ones I've mentioned here. All of these theories assume that space-time is fundamental, and that particles in space-time are fundamental. These particles, complicated connections of them, interactions of them will lead to macroscopic objects like brains, and brains will give rise to consciousness or to the illusion of consciousness. Some of these you could take as functionalist. They may not have a physicalist assumption, but they assume that somehow some functional properties give rise to conscious experience or the illusion of conscious experiences. Panpsychism assumes that space-time is fundamental and the particles are fundamental, but that their ultimate nature also involves consciousness. So panpsychism also assumes that space-time is fundamental and its particles. But the physicists disagree. They disagree with us. They say space-time is doomed, and I'll just give you a couple of quotes. Nathan Seiberg at the Institute for Advanced Study says that I'm almost certain that space and time are illusions. These are primitive notions that will be replaced by something more sophisticated. Nima Arkani Hamed at the Institute for Advanced Study says the very notion of space-time is not a fundamental one. Space-time is doomed. There is no such thing as space-time, fundamentally, in the actual underlying description of the laws of physics. This is remarkable because physics has been about what's going on in space and time. David Gross, a Nobel laureate at UC Santa Barbara, says there is no operational meaning to distances smaller than the blank length. And he's referring to clear experiments and implications of modern physical theory that when you bring quantum theory and gravity together, when you try to make measurements that's smaller than the Planck scale, it makes no sense at all. There's simply no operational meaning to such measurements. So it's not that there are pixels at the Planck scale, it's simply that space and time make sense, make no more sense. Now, physicists have said that space and time are not fundamental, and they're finding structures beyond space-time. They're quite successful at that. It turns out that evolution by natural selection agrees. We can use evolutionary game theory to ask the technical question, does natural selection favor true or veridical perceptions? That is, perceptions that are homomorphic to structures in objective reality. And we don't have to wave our hands, we can prove theorems. Chetan has proved some theorems, and we've done some simulations showing that veridical perceptions almost surely go extinct. The probability that natural selection has shaped our senses to see reality as it is in whole or in part is precisely zero. So what, evolution has shaped our senses to be adaptive guides to behavior, period, not to show us the truth. They are adaptive guides to behavior. So just like a virtual reality interface, the headset, is an adaptive guide to playing a game, our senses are an adaptive guide to playing the game of life, but they're not there to show us the truth. They're there to hide the truth and guide adaptive behavior. So space-time and its particles are not fundamental, nor are any objects in space and time. That's what our best pillars of science are telling us now. And this entails something stunning, that reductionism is doomed. The idea that we can go to smaller and smaller scales in space and time and find more and more fundamental laws and entities, that has been successful, but it's come to its end. Reductionism is doomed, as the physicist Nima Arkani-Hamed says. So the entire reductionist paradigm that fundamentally physics is given by some stuff at the ultra most microscopic distance scales, and that somehow we just have to go there to see what's going on, is ultimately false because of gravity. So physicists are now looking for the non-reductionist approach, and they're finding all sorts of non-reductionist features in physics. So the idea that the fundamental particles, the quarks and the leptons and the bosons, are the fundamental aspects of reality and everything can be reduced to that, is going out the window. Physicists are giving up reductionism. But in our work on consciousness, we typically assume this. We assume space-time is fundamental. We assume fundamental particles are fundamental, that macroscopic objects such as pyramidal neurons that are complex combinations of particles are real objects that exist independent of being observed, and that ultimately macroscopic objects like brains are made out of these fundamental particles, and they give rise to consciousness. This is the framework in which almost all of the research in consciousness is being done. Again, but what's remarkable about this research is something that Steve Pinker points out in his 2018 book, what I call the stipulation problem of consciousness. Pinker likes the global workspace theory, and he talks about it, but he says the last dollop in the theory, that it subjectively feels like something to be such circuitry, may have to be stipulated as a fact about reality where explanation stops. And he's pointing out that the global workspace theory is a wonderful mathematical or at least computational theory, and but it can't explain any specific conscious experience, like, for example, the sound of a saxophone. What workspace state or connectivity must be the sound of a saxophone and couldn't be the sound of a trumpet. And similarly for the other theories, integrated information theory, even if you take it as a functionalist theory and not a physicalist theory, what integrated abstract function must be the smell of a rose and could not be, in principle, the smell of garlic. There are no principled accounts for specific conscious experiences. And the same thing for orchestrated collapse models. What specific orchestrated collapse of microtubule states must be the taste of chocolate and could not be the taste of vanilla. All these proposed connections in these theories are entirely stipulated, as Pinker points out. So that's what I call the stipulation problem. We have to stipulate global workspace or integrated information or orchestrated collapse, and we have to stipulate the conscious experiences that are connected with them. It's stipulation on both sides. So but reductionism is doomed. And so this whole approach of trying to start with either functionalist or physicalist or functionalist embedded in physicalist frameworks, the physicists are telling us that that's not the way to go. They're also telling us something else that's surprising, and that is that quantum theory is not fundamental. And that was a big surprise to me. But this is Nima, again, from Institute for Advanced Study, saying, so there's some way, some other structure that we're looking for, and some other way of thinking about interpreting the structure that will let us see space-time and quantum mechanics emerge simultaneously and joined at the hip. So the idea is, again, that it's not just that space-time is doomed, but quantum theory is doomed. And the deeper structures like the amplituhedron, it turns out, give rise to space-time and unitarity of quantum theory. So quite striking. So now the physicists are using this, and they came to this kind of point of view from their work on scattering. At Large Hadron Colliders, you might have 2 gluons smash into each other and 4 gluons go spraying out. And the physicists are trying to get the probabilities, what they call the amplitudes, for these various scattering events. And when they did this using the standard space-time techniques with Feynman diagrams and so forth, 2 gluons in, 4 gluons out, which is apparently a very common kind of interaction, turned out to be hundreds of pages of algebra in millions or billions of terms. So the theorists were asked by the experimentalists to give them something easier to work with. And in 1986, Park and Taylor discovered that when you let go of doing the Feynman diagrams, somehow they got this magical formula. They didn't know where it came from, but the hundreds of pages turned down into one term that gave you the right amplitude. It was a true stunning, call from somewhere. So over the next few years, they made all sorts of successes and found all these formulas. And finally, less than 10 years ago, in 2013, the physicists discovered this structure called the amplituhedron. It's a structure beyond space-time. It's built out of positive Grassmannians, as we'll talk about. And the volumes of this structure actually give you the scattering amplitudes. And so what they found is when you let go of space-time, the computation of amplitudes becomes much simpler, and they discovered new symmetries. There's something called the dual conformal symmetry and infinite Yangian symmetry that you can't see in space-time. So the physicists find you let go of space-time, the math becomes easier, and you see new symmetries that you couldn't see in space-time. So space-time is doomed. So, but what's remarkable to the physicists was that these Onshell diagrams that allow them to compute the scattering amplitudes that are based on the positive Grassmannian and so forth are fully determined by permutations. That was pretty stunning. So behind space-time are these beautiful structures, and behind the structures are permutations. So the physicists have found, to summarize, space-time is doomed, but you can let go of space-time and you can still do good work, and you find these structures, the amplituhedron and positive Grassmannian, and behind them are kind of permutations called decorated permutations. So I'm going to tell you what decorated permutations are. If you have a set of entities 1 through n, the standard permutations, of course, are just bijections of the set to itself. A decorated permutation is a slight generalization. It's a mapping sigma from 1 through n to 1 through 2n. So it's into twice the size of the range. And for any element in 1 through n, its permutation sigma, so any element A, its permutation sigma of A is always a permutation to the right. You always permute to a bigger number. So A is always going to be less than sigma of A, which will always be less than A plus n. So if you wanted to go to a number less than n, if you wanted to go, for example, to n minus 1, you'll actually go to 2n minus 1. So but the thing is that the number beyond n, if you have a number beyond n in your permutation, we interpret it as the regular permutation mod n. So that's a decorated permutation. You just always permute to the right and you wrap around essentially. When you go past n, you wrap around, but you keep going with the larger number to represent it. So just a brief, so 1, 2, 3 going to 2, 3, 1 would be changed decorated permutation to the permutation 2, 3, 4, because 3 going to 1 is going backwards, so you have to go forwards. And so when you go forwards, you have to go to 4 to get back to 1, mod 3. And there's other examples like this, but I think you get the picture. So they've been led to the amplituhedron and these decorative permutations by their study of positive Grassmannians. And it turns out the positive Grassmannians have a nice cell decomposition based on the decorative permutations. So here's the positive Grassmannian of G of 1, 2. And it's basically the positive Grassmannian is the set of all k planes in n dimensions with positive slope. So it's G of k, G plus of k comma n is a set of all k planes in n dimensions having positive slope. And so here's G1, 2, which would be all the lines in the right quadrant with positive slope. So that's what the amplituhedron is based on, is various forms of this positive Grassmannian. So the Grassmannian, I should now tell you a little bit about the positive Grassmannian in mathematical detail. So first, the Grassmannian itself is the set of all subspaces V of dimension k in some complex space N. And for any particular element C in the Grassmannian GRKN, you can give it for example, a matrix representation is not unique, but you can give it a matrix representation. And you can define what are called Plücker coordinates for this representation. The Plücker coordinates are any k by k submatrix. So it's a determinant of any k by k submatrix. So you might take the first column and the third column. That's a k by k matrix, 2 by 2 in this case, and take its determinant. For each possible submatrix, you get a determinant, and these are called the Plücker coordinates for the matrix. And they're the coordinates for that subspace. The positive Grassmannian consists of, and we call it the positive Grassmannian, it's really the non-negative Grassmannian, but everybody calls it the positive, is a subset of GRKN of the reals where the Plücker coordinates are non-negative. So again, it's the idea of the positive slopes or non-negative slopes. And it turns out that with the positive Grassmannian, you can give a cell decomposition of any positive Grassmannian using the decorative permutations I described, and all the cells are homomorphic to open balls. So it has a nice topology. So this was a beautiful result. And so the positive Grassmannian is connected with decorative permutations as follows. You can take a representative matrix for any positive Grassmannian and think of it in terms of columns. So this is 2 comma n, 2 comma 5, 2 comma 4 in this case, but we can think of these as column vectors. Each column has 2 elements, and there's n column vectors. So for each column 1 through n, what you do is you assign the decorative permutation as follows. If A is the 0 vector, so both entries are 0 in this case, then you just say the sigma of A is the identity. That's called the first declaration of the identity. Sigma of A equals A. If A is not in the span of all these vectors, so if your vector A is not contained in the span of all the other vectors, then you give that vector the decoration, which is called the other decoration of the identity, A plus n. That's the second decoration of the identity. Otherwise, if it's not the 0 vector and it is in the span, then you let sigma of A be the first element B in 1 through n, such that the vector C sub A is in the span of C sub A through C sub B. So essentially, you're using the decorative permutation to tell you the spans of these various vectors, or to say when they become linearly dependent on the remaining vectors. So from these, the physicists can give you what are called Onshell diagrams, And I'll just go into briefly there for 3 particles, there are only 2 amplitudes. And they're represented by a white dot for one kind of amplitude and a black dot for the other. And the amplitudes have these 2 different decorative permutations. 1, 2, 3 goes to 2, 3, 4, and 1, 2, 3 goes to 3, 4, 5. And the way they build up Onshell diagrams for general particle scattering is by amalgamating these 3 particle amplitudes into more complicated diagrams. And the way you interpret these diagrams is to get the permutation, if you start for a number like 1, to get its permutation, you go in. If you see a white dot, you always go to the left. If you see a black dot, you always go to the right. So here, I go in, I'm at 1, go see the white dot, I go to the left, that goes to 2. So 1 goes to 2. 2 goes into 3, 3 goes to 1, which is 4 for the decorated permutation. And if it's the black,
it's okay. It's back. It's back. You can.
did you lose me?
No, you're good. Yeah, we did, but you're back.
Okay.
Yeah.
Okay, so with the white vertices, you always go to the left. 1 goes here, goes to 2, 2 goes left to 3. For the black vertices, you go to the right. 1 goes to 3, 3 goes right to 2, 2 goes right to 1. But of course, 1 is actually 4 in the decorative permutation. So that's the idea. And you can take these 3 particle amplitudes. Each one of these dots is a 3 particle amplitude, and build up. This is 4 particle scattering. You can build up as many particle scattering as you want to from these. And the way you do it is you for any permutation. So here's a permutation 1, 2, 3, 4, 5 for 5 particle scattering. Here's the decorative permutation of it. And what you can do, there's a canonical way of using decomposing that decorative permutation into adjacent transpositions, which I've done here, but I won't go through it. And for each adjacent transposition, it turns out you can write down a pair of 3 particle amplitudes that you build together to amalgamate the entire Onshell diagram for the n particle scattering. And from that, it turns out there's a canonical way of associating a differential form, and you get the amplitudes. So space-time is doomed. The physicists have found, though, that they can let go of space-time, and they're finding the positive Grassmannian and amplituhedron beyond space-time, and behind those are these decorative permutations, which seem to be driving the whole story. Also something called helicities that I should mention as well. But as I mentioned, it's like this monolith beyond space-time. There's no dynamics. It's just a static structure sitting there. Who ordered it and why this particular structure? Physicists don't have an answer. Now I'll turn to consciousness and theory of conscious agents. And I've talked about this before, so I'll be brief. What we propose is based on what Pinker points out in the stipulation problem of consciousness. All current theories of consciousness stipulate physical systems or functional systems, and then they also have to stipulate the conscious experiences. So here's this integrated information, take it as a functional description, and this integrated information, to say that it's the taste of chocolate, that's a further stipulation. Well, our attitude is, if we're going to stipulate conscious experiences, then let's stipulate nothing else. That's the bottom line. If we have to stipulate the connection with conscious experiences, then let's obey William of Occam's razor, and let's stipulate nothing else. We'll just start with conscious experiences, and we'll go back and boot up space-time, and we'll boot up these functional properties. We'll only assume the conscious experiences. So the advantage of this is the other theories assume they stipulate space-time and particles and functions, and then they stipulate conscious experiences. We will only stipulate conscious experiences, and we will then take on the task of booting up space-time and the functional properties. To boot up a theory of consciousness, of course, is a tall order. There's lots of things a theory of consciousness should do. This is a small list, but William of Occam tells us to take just as few as possible. So what we have done is to take just the idea that there are conscious experiences, and that conscious experiences influence. So we define what we call a conscious agent, and it has conscious experiences, and those conscious experiences we'll see influence other agents' conscious experiences. So our definition is that a conscious agent is a 7-tuple WXG PDAN, where X really represents the experiences of the agents. G represents how those experiences are going to affect the experiences of other agents. And W is going to be the collection of other agents. So we represent the experiences of agents, the actions that they might take, and then the whole collection of other agents with measurable spaces. And there's a mapping P, a perception map from other agents to this agent's experiences, a decision map that determines that the action is going to take, and then an action map that goes and affects the experiences of the other agents. And these are Markovian kernels, which was the least committing mathematical structure we could come up with. And then we have an integer n, which counts the number of decisions that this agent makes. So the conscious realism thesis is that the entire world consists of conscious agents. That's our ontology. And so here's a small network of two interacting conscious agents, the experiences of one agent and its actions affect the experience of another agent and its actions. And we can get loops of agents. We can have 4 agents, or we can have countless. We could have an infinity of agents. So it's a network theory of consciousness where all the links are Markovian kernels. So when you have agents that are interacting, it turns out that they combine. It's just it turns out the definition of conscious agents entails this. In simple case where they're just interacting is a tensor product, but we'll see that they have more interesting combinations later on, where we call them fusions. So if all agents, when they interact, or even if they don't interact, form new agents, there is in some sense one agent, but we can never get there because of Cantor's hierarchy. We could never actually write down that one agent because we'll always get, as we combine agents, we'll just climb up Cantor's hierarchy. So this always points to a Mount Everest of an interesting one consciousness, but we can never get there through the mathematics. So in the background, you can see there's a network of conscious agents. And the idea then is that, well, first it's trivial to show that the network of conscious agents is computationally universal. So anything a universal Turing machine can do, these conscious agents can do. But they're not limited to computations. The measurable sets on which the Markovian kernels are defined need not be computable. So this is not limited to computation. So, but anyway, anything that Turing machines or artificial neural networks can do, conscious agent networks can do. So we can boot up, even though the theory of conscious agents has no notion of self, learning, memory, problem solving, intelligence, all those things can be built up by networks of conscious agents. So we only start with the assumption that there are experiences, and the experiences influence the experiences of other agents. That's all we assume, and we're forcing ourselves to build up everything, including the notion of a self, if you want to have a self, and so forth. So it turns out with these conscious agent networks, as I mentioned, when you have 3 or 4 or n agents interacting, a good way to describe them from our framework is with Markov polytopes, M3, M4, M5, and I'll talk about that in a moment. And then we're going to show a new contribution to mathematics. It appears that these Markov polytopes have a canonical mapping into decorative permutations. There's a bijection of the cell structure of Markov polytopes with decorative permutations. And we'll connect this with the decorative permutations that the physicists have found. So the way to see this Markov polytope, the easiest way is to take what we'll call the qualia kernel. So we'll take a conscious agent, and what we'll do is we'll create the new kernel D followed by A followed by P. So we're going to start with the experience of an agent X. We'll do its decision kernel followed by its action kernel, which is affecting all the other agents, and then its perception kernel, which then changes its experience. So the PAD kernel really is mapping the experience of this agent at time 1 to its experience at the next time. That's what so it's a qualia kernel. It gives you the sequence of experiences of this agent as it interacts with other agents. So suppose I have 2 conscious agents, and one agent has only one experience, the experience of red, the other one has the experience of green. Now we want to look at their possible interactions. Well, So we're going to write down a qualia kernel for the combination of the two agents, and here it is, Q of xy, where x now is the probability that this new agent experiences green, given that it's currently experiencing red. And y is the probability that the new agent here will experience red, given that it experiences green right now. Now, if these probabilities are 0, then this will be the identity matrix, and the two agents will be effectively independent. They're interacting not at all. But as soon as we crank up x and y to be non-zero, then we get an interaction between these two agents, and we start to get some interesting combinations of the agents. And so we can ask, what are all the possible combinations that these agents can have? Glad you asked. Here it is. It's the Markov polytope M2. So here we have on the x-axis, we're cranking up one interaction along the x-axis, we're cranking up the other interaction on the y-axis, and the whole Markov polytope M2 then is giving us all possible interactions. So here we see the identity matrix, no interaction at all. On this side, we see the not matrix. They're cycling back and forth, and then these other two matrices. Now, what's interesting is we can compute the kernel flows. When you take a kernel and you like P or kernel Q, and you take Q times Q and then Q times Q times Q, you'll get a new kernel. And it turns out you'll always, as you do that, Q to the n, you'll always go along a line. So for example, starting at the identity matrix, when you do that, you'll go along this green line, but you'll always go along these lines. But what's interesting is the kernel product actually goes to 0, becomes stationary. QQ equals Q along this horizontal, the cross diagonal here. We call this the fusion simplex, and I'll talk about that in a moment. But what's interesting is that all the kernel flows go to this point, they stop, and you can see the kernel flows come the opposite direction. So the kernels are flowing this direction from that part of the Markov polytope, in this direction from this side. This is what we'll call the helicity of the flows. So all kernels along a particular ray have the same asymptotic behavior, which is captured by this diagonal. These are the asymptotic behaviors of these kernels, and that's where they satisfy mu q equals mu. This diagram gives you all the blendings of the colors of the kernels. And so you can see how the kernels are blended, and I'll give you a little bit more detail on that in just a moment. So I just want to point out that, again, these flows, we can look at these sort of the derivatives. They're actually difference quotients, but the derivatives of these kernels. And when we look at the magnitude, I'm going to look at the magnitude along this green line. I'll go along it this direction all the way to the end. And here's the plot. So as I go from the identity matrix to the fusion complex, we get this magnitude of the derivatives. And then as we go from there to the not operator, the very, very different. So the helicities are positive and negative, but the profiles are quite different. So now we'll talk a little bit about the fusion of agents in qualia. So here's the matrix again. At that cross diagonal, where the agents actually become, where the kernels become stationary, QQ equals Q, then the matrix drops rank. And we can write it as 1 minus alpha alpha, where alpha equals x equals 1 minus y. So the kernels drop rank, and we take that mathematical dropping of rank as saying that the agents not only, the two conscious agents not only combined, they now have fused. So we distinguish between combining agents and fusing agents. When the kernels drop rank, and you can see as we have n agents, 10 agents, there'll be all sorts of ways that you can combine and fuse or partially fuse. It's quite an interesting structure. But here in this particularly simple case, just to make it, the idea clear, so we take alpha. When alpha is 0, we get the first agent with its red experience. When alpha is 1, we get the second agent with its green experience. But for any alpha in between, we get a new agent. So pick one in the middle. These are brand new agents with brand new qualia. So fusion is different than just combination. It actually leads to brand new agents with new qualia. With 3 agents, that fusion simplex is now a 2 simplex, and these show illustrate all the new colors that come from this kind of fusion. So it's not just combination, it's actually fusion. So now I want to talk about how to get from the conscious agent theory and Markov polytopes to decorative permutations. So if I start a Markov kernel in some state I, and if I can get it to some state j in n steps, if there is some n for which that's a positive probability, then we say that I leads to j. So if I leads to j means that there's at some point, at some step number, you can get from state I to state j with positive probability. Now, if I leads to j and j leads to I, we say that they communicate. So we get, this is an equivalence relationship. So you can take, for any Markov kernel, a Markov kernel carves the state space into communicating sets, equivalence classes. I won't go into this, but for this Markovian kernel, those are the communicating classes. And so you can write the communicating class as the set 1, 2, 3. And I have other examples, but for time, I'll skip. But you get the idea. So here's how, this is what we think is a new mathematical contribution that is the mapping from Markov polytopes to decorative permutations. Here's our algorithm. For each state A of the Markov chain, 1 through n, if A is transient, then sigma of A equals A. That's the first declaration of the identity. If A is absorbing, so A, when you get into the state A, you stay in state A permanently. Then we give it the second declaration of the identity. Otherwise, the declaration is the first element B in 1 through 2n, such that A through B contains the communicating class of A. So we're using the decorative permutation to keep track of the communicating classes. So for the positive Grassmannian, they were keeping track of linear dependence among vectors. Here we're keeping track of the communicating classes of the various states. And we can go into it, but I think you get the idea. So we have a way of mapping decorative permutations, Markov polytopes into decorative permutations. Here it is for M2. So here's the identity. It gets its own class, the horizontal line here, and that corner get another class with the decorative permutation 1, 4. So we take M2 and any Markov polytope, and we give a canonical cell decomposition that's labeled by decorative permutations. The reason we did that was we wanted to make connection with physics, right? The physicists are saying, if you want to connect with us, the deepest thing we found are decorative permutations. And so that's why we started, we had the Markov polytopes. We said, well, if the physicists say we need decorative permutations, is there a way to start with Markov polytopes and get decorative permutations? And we discovered, to our surprise, yes, there is. And so the idea then is that we have the Markov polytopes, and they do lead to decorative permutations. So that gives us a chance to connect with physics and to connect with scattering amplitudes. And we want to actually connect with their Onshell diagrams. And so what we need to do is to show where there are there's these 2 3-particle amplitudes, the white and black vertex things here. We need to show where those come from. And then, from that, we can build up any Onshell diagram that we want. Here's our conjecture. We were led to this conjecture by the decorative permutations. It forced us to look at this particular Markov polytope. It's M3. To be clear, it's the space, it's the polytope consisting of all 3 by 3 Markovian kernels. So it has 27 vertices. The number of vertices for m to the n, m sub n is n to the nth power, so n to the n vertices. So this is 3 to the 3rd, which is 27. So there's 27 vertices, which we've shown here. And what's interesting is there, and Chetan is going to go into this in his talk, little pitch for his talk, there are 3 caps on this. There's an odd permutation cap, I'm sorry, an even permutation cap here, an odd permutation cap here, and the identity cap here. Basically, almost a third of the vertices are involved with the even permutation cap, a third with the odd permutation cap, and almost a third with the identity. There's only 6 left in the middle. And what Chetan will show is that there are these interesting flows of different helicities. So there's a flow this way from the even permutation cap and a flow this way from the identity with opposite helicities, but they meet right here at the 3-dimensional, at the 2 simplex that I showed you with all those, the 3 colors, or the red, green, and blue, and all the colors in between. That's what this is. It's that 2 simplex where everything fuses. So they all converge. Most of the, a lot of the flows converge to that at a single point. And Chetan will go into the details on that. So what we're arguing is that this flow here is one of the 3 particle amplitudes, corresponds to that, and the other flow here corresponds to the other 3 particle amplitude that the physicists have. And so what we're saying is, to the physicists, you've given us these static structures. Here is a world of dynamics behind your static structures. Here's what's going on behind those black and white vertices. And here's a little picture of the flows. So the idea is that this flow, this is one helicity, that's the other helicity, that goes to one 3-particle amplitude. Here's the other flow with 2 different helicities going to the other amplitude. And then from that, we can build up any amplitude. So that's M3. For 4-particle scattering, we would use M4. For 5-particle scattering, we'd use Markov polytope M5 and so forth. And I'm just going to look at one plane here. It's the plane. I mean, this is a really complicated structure. Chetan will go into it in his talk in great detail. But just take the identity matrix, the even derangement, the maximal even derangement, and the maximal odd derangement, and look at that triangle, that plane. And we can then look at the Markov flow. So we can take QQ minus Q, look at that derivative. And it turns out we get these interesting flow patterns. And in this particular case, they meet at the very center of the fusion complex. So that would be equal parts red, green, and blue, right? And so this is, you have to think of this as a 6-dimensional space. So that's why I have a nice graphic for you. I have to do this a little bit at a time. So this is possible for this thing to only intersect the fusion simplex in one point, and so they do. So we're getting what we're calling the flow from like one of the 3-particle amplitudes. Here's the other 3-particle amplitude. And we're seeing the flow. So this is all sorts of detail that the physicists don't have that's behind their amplitudes. So just to show you that the difference, here's the positive Grassmannian G of 1, 2 that I mentioned before. It's all the lines in the plane that have positive slope. We can put that on top of the Markov polytope M2. See all the richness of this Markov polytope M2 with all the flows. When we put them together, basically what the physicists are dealing with is just the positive Grassmannian, is just the bare bones skeleton. The Markov polytope M2 has all this rich dynamical detail, and this will be true for M3, M4, and so forth. So we're proposing that the physicists have made great progress with the positive Grassmannians and the amplituhedron that's made out of them. There's this rich world of dynamics that comes from consciousness that's underlying it. And even if the physicists are not interested in consciousness, say that we couldn't care less about consciousness, we can just say there's a dynamics of something beyond space-time, and here's the dynamics as captured by Markov polytopes, and you need to study it. So now back to consciousness. So conscious agent networks, we claim are fundamental. They have canonical representations as in Markov polytopes and in decorative permutations. So the bridge, the physicists have let go of space-time. It's not fundamental. But they didn't throw up their hands. It's actually, they're having a lot of fun. They've discovered new structures like the positive Grassmannian amplituhedron and decorative permutations beyond space-time. We're starting from the other direction. We're starting with consciousness. We found Markov polytopes. And recently, just in the last couple of weeks, we discovered a way to represent them with decorative permutations. We're proposing that they meet in the middle with the M3, which gives you the two fundamental amplitudes for physics, the two three-particle amplitudes, but more generally, they'll be meeting at the Markov polytope M sub n for any n particle scattering that the physicists are interested in. So the idea then is we start with consciousness beyond space-time. We have not stipulated anything at all about space-time. We stipulate only consciousness, and we get a map from consciousness through decorated permutations of Markov polytopes all the way into space-time, because now we get to use all the work that the physicists have done. So we don't have to stipulate space-time and its properties. We don't have to stipulate particles and their scattering. We get them by starting only with consciousness and only the bare minimum assumptions about consciousness. So we solve the stipulation problem of consciousness by starting this way and using the work that the physicists have done. So that's our basic bridge between a theory of consciousness qua consciousness that makes no stipulations about particles or physics or functions or anything like that. We don't need all those stipulations. We just start with consciousness qua consciousness, and then we boot up space-time and its properties and its scattering amplitudes by connecting with what the physicists have done beyond space-time. So open problems, Shaitan is going to give you a lot of work that's beyond what I'm talking about here. I'm going to mention some basic problems, and then Shaitan will mention some more basic problems. When you do a Google search, there's almost nothing done on these Markov polytopes. I was absolutely stunned. I don't even know the formula for M sub n for the number of facets. We know the number of vertices is n to the n. What's the number of facets? I have no idea what the number of facets for the Markov polytope M20 is. There's just no formula for it. And there's almost no, so stunningly, these basic structures have not been mathematically explored in much depth at all. So for the mathematicians out there, we're coming hat in hand and saying there's this whole world to explore. And I'm betting that if our conjecture is right, the physicists will be interested in exploring this to find out what's underlying their amplitudes. I'd like to figure out how we get the differential forms that the physicists use for their scattering amplitudes. I would like to, we've hinted at helicities of the Markov flows. I would like to tie them to the helicities of particles in quantum physics. Energy momentum. There's an interesting hypothesis that maybe the classes that we've talked about here in the communicating classes in Markov chains correspond to the energy momentum classes. So the conservation of energy momentum in physics corresponds to that. Once you're inside a communicating class, you stay inside of it. So that's an interesting way that we might be able to go between consciousness and physical things. The distinction between mass and massless particles in physics. What is that? And maybe, for example, it would correspond to dynamics in consciousness that's involved only the vertices of these Markov polytopes. That would be the massless. And once you go inside any of these polytopes, you get massive dynamics. But again, these are conjectures. And again, then, for example, to look at two particles in, two particles out, four particle scattering in physics, we need to study M4. And that would be one of the next things we need to do. Is the simplest thing we could do is to study M4. So with that, I'd like to thank my many collaborators, and in particular, again, my collaborators on this are Chetan, Prakash, Robert Prentner, and Manish Singh, and these other people I'd like to thank for help in various ways over the years. So thanks.